Good morning all. Today we'll be learning about the geomagnetic effect. So geomagnetic effect, that is a Earth's magnetic field effect on what? On the cosmic ray particles. So the theory tells if you have a magnetic field and moving charged particle, then the magnetic field exerts a force on the moving charged particle. This force is always perpendicular to the direction of the moving charge field and also to the direction of motion of the charged particle. And we all know that cosmic ray particles are charged particles coming from the outer space. So how does the magnetic field of Earth affect this cosmic ray particles? If the cosmic ray particles are coming in the direction of magnetic field, that is Earth's magnetic field, then we know that no force is exerted on the particles. Or we can say that if the particles are moving along the Earth's magnetic axis, it will not be deflected. Okay. Again, now if the particles are moving at right angles, that is in the perpendicular direction of the Earth's magnetic field, then you can expect the charged particles to move along a circular path. So now you have 0 degrees and 90 degrees. What about other degrees like any arbitrary degree, 20, 30, 40? Okay. Along any arbitrary direction, what happens? This cosmic ray particles, when it comes into Earth's magnetic field, it spirals along the line of force. So these are 3 conditions by which the Earth's magnetic field can affect the cosmic ray particles. So we can say that some particles will be deflected away from and some others will be pulled towards the Earth. Particles moving along the Earth's magnetic axis will not be deflected. Then the effect of this Earth's field is to reduce the intensity of the cosmic rays in certain latitudes. Okay. Next we will be dealing with the Van Allen belt. Coming back to the upper atmosphere, that means at high altitudes, we can see that the low energy particles are due to 1. Primary cosmic radiations, secondary cosmic rays, that you know how it is produced by the interaction of the nuclei of the upper atmosphere gases with the primary cosmic radiations, and third, it is due to low energy particles which is emitted by the sun. Now these charged particles get trapped between the magnetic field of the sun, okay, and the Earth, and then they get confined in the shape of a donut, or usually Malayalis are familiar with udinu vada. It is that shape. Okay, it's more or less the donut and the udinu vada are of the same shapes, so they get confined into the donut shaped belts. It comprises of inner Van Allen belt and also the outer Van Allen belt. So it is after a scientist named Van Allen. Okay. So here you have a schematic picture of it. You can see that we have Earth at the center. There is a magnetic field by the Earth and also the magnetic field of the sun, which is influenced on it. And these low particles, charged particles, get trapped within these 2 magnetic fields and forms a donut. So you have inner Van Allen belt and the outer Van Allen belt. The inner Van Allen belt consists of protons, okay, while the outer Van Allen belt consists of low energy protons and electrons. So how do these, it forms a donut shape? It is because of uh, these charged particles get reflected to and fro, and also they spiral along the magnetic field lines. So this is how that radiation belt is formed. Next in the line is the east-west asymmetry. The intensity of cosmic rays which comes from west is about 10% higher than from the east. So it is that those cosmic rays coming from west is 10% higher than that of the east. Again, they have seen that or observed that if the cosmic ray particles are positively charged, then the Earth's magnetic field deflects a large number of particles from the west. And for the negatively charged particles, it is the opposite effect, that is, it gets attracted. This difference in intensity of cosmic rays reaching the Earth's from western and eastern side is called the east-west symmetry. So it's very simple. So what we have here is the cosmic rays coming from west is about 10% higher than that of the east. And again, those cosmic rays which are coming from the west, if it is positively charged, it will be deflected. If it is negatively charged particles, it will be attracted. So this difference in intensity of cosmic rays between the eastern and western direction is known as the east-west symmetry. Next, coming to the altitude effect. They have made 3 observations. 1, the cosmic ray intensity is minimum at the sea level. So at sea level, the cosmic ray intensity is very minimum. Secondly, what they found is that the cosmic ray intensity increases with increasing altitude up to the height of 20 to 25 kilometers, and thereafter the intensity falls. Okay, up to 20 to 25 kilometers the intensity of cosmic ray increases, and after 25 kilometers the intensity is declining. The third observation which they made is that the intensity of the cosmic rays at one given altitude increases with geomagnetic latitude. Okay, so it is a maximum at 16 degree north and minimum at 30 degree north for one particular altitude. And the explanation is given as follows, that is, the cosmic rays beyond 25 kilometers consists of mainly protons and small percentage of helium nuclei. So what happens? The primary cosmic rays containing all such particles, when they come to the Earth, they interact with the nuclei of the atmospheric gases. And when they interact, what happens? Secondary particles are formed with low energies, and thus the total intensity of the cosmic ray increases. And also we know that as altitude decreases, the intensity of cosmic ray decreases, and we can see that we have already seen that at sea level these rays contains only very small number of high energy particles. So that was the explanation for the observations which we made in the case of a altitude effect. Okay, thank you all.